the sun-drenched garden of Down House, insects buzz a low symphony as they dip methodically from bloom to bloom. The stems of wildflowers wave gently in the warm breeze, and a barn cat stalks the fat pigeons that amble gracelessly across the lawns. It is an idyllic scene, but one that goes unnoticed by the usually attentive occupant of the stone country house. Because Charles Darwin is in mental agony. Instead of his usual calm, contemplative walks around the dappled perimeter of the estate grounds, he now irritably paces the creaking floorboards in his darkened study. The shutters are drawn against the summer sunlight, all the better to focus a tormented, overtired mind. But it is no use. No amount of pacing will solve Darwin's problem. He mutters under his breath and storms towards his desk. Sweeping aside the crumpled papers, he dips his pen and scratches out a final line. The case at present must remain inexplicable, and may be truly urged as a valid argument against my views, here entertained. The year is 1859, and Darwin is rushing to complete the manuscript for his book on the origin of species. For the last 25 years, since his time as a naturalist aboard the HMS Beagle, the scholar has been consumed with the connections between living things. Everywhere he looks, he sees interrelationships between animals, plants, and the non-living world, which are fundamental in shaping the way individuals look and behave. Fundamental, in fact, to the way they came about, to their evolution. For 2 decades, he has worked and reworked his theories, but ultimately, he is prevaricating. He's not the kind of man to rush and publish a provocative idea. He wants every loose end tied up, every problem to have a solution, and every possible argument a riposte. But now his hand has been forced. Another young naturalist, Alfred Russel Wallace, has also drawn the same conclusions about the evolution of living things, and has already published his preliminary ideas. Darwin must consolidate his theories and get them to print, or else decades of quiet contemplation will have been for naught. And that means he must publish before finding a solution to one of his biggest conundrums: the origin of animal life. Darwin's theory of evolution by natural selection describes how new species come about as a result of variation and competition within living populations. New characteristics are acquired gradually and amplified by continued pressure from the living and non-living environment. Over centuries, the beaks of finches can transform to suit the available food sources on different Galapagos Islands. Over millennia, giant glyptodons, now extinct, transform into their smaller cousins, the armadillos. All through the living world and the fossil record, Darwin sees evidence of gradual change. And with enough time, those changes can accumulate to produce the complex and diverse animal forms that populate the world today. But time is not on Darwin's side. Not just in this new pressure to publish, but in undertaking the origin of these complex animals in the first place. According to his theories, animal life should take a long time to arise, gradually developing from simpler forms, acquiring unique characteristics piecemeal. But the fossil record tells a very different story. It shows none of those simple animals, no gradual transition. Instead, the first animal fossils make a sudden, explosive entrance into the fossil record, without warning or preamble. Tracing the layers of rocks back through time, one moment animal fossils are there, and the next, they're not. It is as if they and all animal life appear miraculously and instantaneously from nowhere at all. It's a serious blow to Darwin's otherwise well-evidenced theory of gradual transformation. And Darwin, being the cautious and anxious man that he is, has lost countless nights of sleep over this conundrum. But there's no solution among his notes, among the fossils scattered around the study floor, or in the sun-soaked garden beyond the shutters. As he wrote in the now finished manuscript, the case must indeed remain inexplicable, at least for the time being. Now, however, we are more than 150 years on from those tortured moments, with a wealth of paleontological discovery and evolutionary theory under our belts. If there is a solution to Darwin's dilemma, it must surely lie among all that accumulated knowledge. Now we are finally equipped with the tools to understand the sudden appearance of animal life in the earliest rocks of the Phanerozoic. Was Darwin wrong, or the evidence merely incomplete? What really caused the Cambrian explosion? This episode of History of the Earth is brought to you by BetterHelp, the online therapy service used by over 4 million people worldwide. Like Darwin in his mental anguish at contemplating the origins of life on Earth, is something interfering with your happiness or preventing you from achieving your goals. Starting therapy can be hard. The right therapist for you might not live in your area, and the face-to-face interaction of therapy can be uncomfortable. BetterHelp connects you with a credentialed therapist who is trained to listen and give you helpful, unbiased advice. All you have to do is fill out a questionnaire, and in most cases you'll be matched with a therapist within 48 hours. If the therapist you're first matched with doesn't feel like the right fit, you can easily switch to a new therapist at no additional cost. All you have to do is fill out a questionnaire, and in most cases you'll be matched with a therapist within 48 hours. If the therapist you're first matched with doesn't feel like the right fit, you can easily switch to a new therapist at no additional cost. Most importantly, you can schedule therapy sessions for times that are convenient for you in whichever format you prefer, be it via phone call, as a video chat, or even via messaging, if that's what you prefer. As Darwin knew all too well, our brains are the most important of all organs, so why not give our minds the proper care and attention they require? If you think you might benefit from therapy, consider BetterHelp. Clicking our link in the description below will give you 10% off your first month and help to support the channel. Thanks to BetterHelp for supporting educational content on YouTube. When Meriwether Lewis and William Clark embarked on their epic voyage across America and back in the early 1800s, they had little idea of what to expect from that wild, uncharted country. Their president had tasked them with the mission to not only seek a passable river route to the Pacific Ocean, but also to observe and document the animals they discovered along the way. The promise of unexplored revenue has always been a great motivator for scientific inquiry, and Lewis took crash courses in botany and zoology to give him a head start in what was already known and what was not. But the party were explorers first and foremost, and their approaches to zoological study was often as wild as the country they charted. In September 1804, somewhere between the Niobrara River in Nebraska and the Teton River in South Dakota, they came across a hillside pockmarked all over with holes. In the quiet before their approach, these holes were guarded by what the explorers described as a village of small animals, who barked a warning before disappearing inside the burrows. Never ones to miss an opportunity to fulfill their scientific brief, Lewis and Clark endeavoured to catch one of these furry critters, and first tried digging down into the burrows after them. But even after reaching a depth of 6 feet, they were empty-handed and changed tack. Only by pouring buckets and buckets of water into the animal's holes did they finally manage to flush one out, trap it, and send it home for study. The party offered many possible names for this new, elusive animal, such as barking squirrel, ground rats, or burrow squirrels. But the name that eventually stuck is still one we use today: prairie dogs. In just 2 weeks, while trekking the 100 or so miles between these two rivers of the American plains, the party encountered 3 more animals new to them: the jackrabbit, the coyote, and the pronghorn. And by the end of their 2-year expedition, the pair had documented some 122 great American animals for the first time. Animals which, it should be said, were already well known to the native tribes of these regions, but were nevertheless a source of endless wonder, inquiry, and inevitably revenue to the settlers. Today, the curious zoologist need not chart the unknown to discover the diversity of animal life that our planet has to offer. A simple stroll along a rocky shoreline anywhere on Earth will suffice. There, sandwiched between towering cliffs that march to the very end of the landscape, and the grey-blue expanse of the open ocean, the deceptively calm waters of rock pools and sandbarred ponds are in fact teeming with animal life. There are sponges, members of the phylum Porifera. Despite looking a little like a melted version of a bathroom sponge, these lumpy, porous encrustations on the rocks are the amorphous skeletons of simple animals. They make their living by filtering the seawater through tiny pores, extracting bacteria and other food particles to feed their simple, rooted bodies. There are the soft, jelly-like tubercles of sea anemones. Above the waterline they sulk, folded in on themselves like resentful pustules in hues of angry mauve and mossy green. But when they find themselves submerged, they unfurl, blooming into graceful, many-tentacled, flowered polyps. But each of these tentacles, swaying gracefully in the current, bears fierce, stinging cells that shoot painful, paralyzing poison at the slightest touch. They are cnidarians, a group of animals defined by their stinging armory, deployed to help them immobilize and catch their food. Many jellyfish, as well as hard-bodied corals whose skeletons break down to golden sand, are cnidarians too. There are arthropods, so named for their pairs of jointed appendages. They include the six-legged insects that flit around in the salty air, as well as 10-limbed crustaceans like crabs that sidle out from rocky hollows to peer back at their observers with alien, stalked eyes. With their hardened exoskeletons, the arthropods are the largest group of invertebrate animals, accounting for over 80% of all known animal species. There are mollusks, another diverse group, whose rock pool representatives might include the sea snails with their striped, coiled shells, or the pointed limpets that cling to the rocks with an iron grip that only tightens further the moment the creature is disturbed. Mussels, whelks, cockles, and oysters offer a molluscan smorgasbord of edible life, too. Oft identified by the protective shells, it is nevertheless the fleshy mantle within that truly defines a mollusk. Small, frilled sea slugs might dazzle with a flamboyant flash of colour as they drift aimlessly in the water, while resting octopuses skulk in the shadows, pulsing colour and texture across their skin as they dream of the open water. Mindless and blisteringly intelligent, they are about as different as two animals can be, and yet both are mollusks. Then there are the spiny punks of the rock pool, the echinoderms. Sea urchins hide in plain sight, the broken outline of their dark bristled shells blending into the dappled light to become the ultimate spiny hazard to unsuspecting waders. They move slowly, defying gravity across rock and sand, powered by hundreds of tiny hydraulic tube feet projecting from the underside of their shells, grazing surfaces free of algae with a 5-beaked mouth suspended in their undercarriage. They are a pastiche of the finest fantastical fiction, and yet few who find their discarded heart-shaped shells are ever aware of how truly odd they are. Echinoderms are unique in possessing a 5-fold symmetry, something which is flaunted by the 5 prongs of most starfish. They too possess the bizarre fleshy tube feet and terrifying beaked maw, but dress up their alienness with a dazzling show of geometry. And there are worms. So many different kinds. One 20th century biologist, John Haldane, once joked that if God created the animals, then he must have had an inordinate fondness for beetles. But considering the major groups of life, that surely must be a fondness for worms. There are annelids, the spiny ragworms that lurk in dark rocky crevices, or the lugworms that leave coiled sand piles on the freshly wetted tidal flat. There are Nemertians, better known as ribbon worms. One such ribbon, known as the bootlace worm, may look little more than a pile of discarded intestines, but claims the title of the world's longest animal, at up to 55 meters long. And there are flatworms, who make a parasitic living on other fleshy creatures. And if this were not enough, not every animal is visible to the naked eye. There are also countless other microscopic forms, each a perfect animal less than a fraction of a millimeter in size. There are bryozoans, who live alongside the sponges in encrusted colonies. They are not one animal, but many, inhabiting a densely packed metropolis of their own making. There are 8-legged, snub-nosed tardigrades, clawing their way through fibrous seaweed in search of their next meal. There are rotifers, with their buzzsaw-like mouths brushing particles into their guts as they stretch and pucker themselves through the water. And there are nematode worms, also known as roundworms, which are found everywhere. These are the most extensively parasitic animals on Earth, and it's been said that if all other life on our planet suddenly vanished, we would still see a shadow of it written in the nematodes left behind. Of course, the zoologist themselves is a part of this animal diversity too, as they crouch to observe the swarming rock pool life. They, like all humans, are a chordate, a vertebrate, a group which encompasses all mammals, fish, reptiles, amphibians, and birds. These large, charismatic organisms, which we doubtless consider first when we think about animal life on Earth, whether it be whales, dinosaurs, ostriches, and monkeys, they are all chordates too. Chordates may be unique in hogging the limelight and in sparking a branch that can ultimately come to consider themselves. But in reality, they are no more preeminent or diverse than their molluscan or vermicular cousins. All this diversity and disparity existing within such a small pocket of Earth's surface is remarkable in itself. But what is perhaps more remarkable is the fact that almost all of these animal phyla, all of this incredible variety, appeared on Earth in a geological blink of the eye. After almost 4 billion years of slow progress, in which life remained microscopic, out of sight and out of the visible fossil record, 538.8 million years ago, large, complex and spectacularly diverse animals burst onto the scene in a blaze of fossilized glory. Within just 11 million years, 20 out of the 35 phyla that exist today appeared in the Cambrian oceans. And not just that, there were other animal groups, types of arthropods and sponges that swarmed those ancient seas and which are now extinct. This was not the stumbling experimentation of quilted flesh that defined the Ediacaran period, but a resounding and definitive breakthrough in animal ecology. The zoologist who found himself within the mid-Cambrian Ocean, perhaps 510 million years ago, would find a diverse and interconnected ecosystem to rival that of any modern rock pool. There are sponges hulking formlessly across the ocean floor, filtering microscopic food particles from the murky waters. There are rudimentary cnidarians lurking inside rough, cup-shaped skeletons as a precursor to the reef-building corals of later times. There are worms that writhe across the seafloor, leaving criss-crossing trails behind them, while others, for the first time, burrow down into the soft muds, disrupting the delicate sedimentary layers and churning organic-rich material up into the water above. And there are plenty of animals that take advantage of that material, like deposit and filter-feeding arthropods and mollusks, of multifarious form and function, sweeping the water clear of every speck of primary nutrition. Meanwhile, sinister shadows cast from above reveal the presence of predatory animals too, who for the first time make a living preying upon their own taxonomic kin. Plus, wherever life thrives, there is also death. And some new animals choose a scavenger's way of life, feasting on the remains of others before bacteria move in to complete the decay. And there are parasites, just as there are today, choosing to leech their life force from the hard work of others. It is the kind of community that will come to exist in habitats all over the world, throughout the Phanerozoic. Although the particular denizens of the Cambrian are often more bizarre and extravagant than any we might see later. A testament perhaps to this golden age of invention and experimentation. There is Hallucigenia, which walks on fleshy, tubular legs while sporting a terrifying mohawk of spines along its back. There is the Canadia worm, flamboyant with iridescent frills all along its diminutive body. There is armoured Wiwaxia, covered in scaly plates and spines as protection from the looming predators above. And among these predators, there is Anomalocaris, which undulates through the open ocean, probing for food with two elongated prong-like appendages next to its disc-shaped mouth. And there is Opabinia, equally terrifying with its 5 eyes and hose-like proboscis that ends in a spined claw. Perfect for dealing unexpected death from above. Much of this Cambrian diversity would have been unknown to Darwin, as he racked and writhed over the origins of animal life. 19th century paleontologists certainly knew of the most successful Cambrian organisms, like trilobites and brachiopods, but this wondrous ecology has only been revealed with discoveries made in the last 150 years. And yet, this modern paleontological treasure has done little to address Darwin's dilemma. Tracing back the Cambrian fossil record to its ultimate beginning, the larger, more complex forms may become more scarce, but there are still animal traces to be found. The rocks at the very base of the Cambrian, belonging to the Fortunian period, are filled with the fragmented shells of enigmatic worm-like or mollusk-like animals. These so-called small shelly fossils are like the diminutive drum roll to the animal symphony that was to come. And yet they too seem to appear without warning or preamble. They may have been the precursors to the staggering diversity of later times, but what were their precursors? What really happened at the beginning of the Cambrian to usher so many fossils, first small and shelly, then numerous and complex, into being? In August 1968, The city of Prague in then Czechoslovakia was filled with an uncharacteristically scholarly crowd. The city, which was enjoying a brief moment of calm amidst a drawn-out political uprising, had been selected as the host for the 23rd International Geological Congress. A chance for geoscientists from across the world to come together and present, discuss and debate the latest scientific breakthroughs pertaining to our planet. And this Congress promised to be a spectacular one. With 3,000 scientists attending from 91 countries and more than 700 pieces of new research on the slate, it was the largest such meeting in almost 100 years. A show of unprecedented collaboration at an otherwise tense time for the world. One of the highlights of the 5-week-long agenda was an in-depth investigation of the Cambrian explosion. The best geoscientists in the world would come together to discuss what had been learned in the 110 years since Darwin's dilemma, to define the exact date at which animal life exploded, and to consider how it could have come about. But it was not to be. On the evening of the 20th of August, at the end of the Congress's very first day, Soviet tanks rolled into the streets of Prague under the cover of darkness. By morning, the invading communists had seized control of all the major transport and power centers in the country, wresting power from the revolutionaries and putting a definitive end to the liberalization that the Czechs had been fighting for months. In that single night, the hopes of the country and of the assembled geoscientists evaporated into thin air. The Congress was cancelled. Scientists fled home, with the optimism of just a few days earlier now cast under a dark cloud. Much of the research and discussion was postponed until the next Congress or later, since ever new topics arose to steal the limelight. In the end, it would be another 15 years before the subject of the Cambrian explosion was revisited. To discuss what had been learned in the 20 years since, evidence points to a sudden explosion of animal life around 540 million years ago. But the best scientists think twice before taking anything at face value. Before considering the very difficult question of how diverse and complex animal life could appear, seemingly out of thin air, they first entertain the idea that there is something missing, some part of the puzzle which would explain what we're seeing without invoking miraculous acts of creation. Something that would suggest that the Cambrian explosion is not truly an explosion of animal life, but rather an explosion of evidence. In the middle of the 19th century, Scottish geologist Charles Lyell was the first to suggest that paleontologists of the time were perhaps not as omniscient as they would like to believe, and that the fossil record still had many secrets to relinquish. He proposed that the Cambrian explosion was merely an artifact of an incomplete record. It was as if we had our hands on Volume 2 of the Encyclopedia of Animal Life, but Volume 1 was still languishing somewhere in the stacks yet to be discovered. Then, around the turn of the 20th century, the American paleontologist Charles Doolittle Walcott expanded on Lyell's hunch, suggesting that there must be missing links out there that showed the gradual evolution of animal life prior to the Cambrian explosion. He was so confident of this assertion that he did what none before him had done and gave a name, the Lapalian period, to the missing period of time in which this supposed animal evolution took place. Prior to the precise isotopic dating of rocks, such a period could indeed be sandwiched between the known eras, whose relative ages are only known by their relationship to one another. Walcott proposed that the animal missing links were confined to an as yet undiscovered Lapalian ocean, which, when uncovered, would sit between the earliest Cambrian and the latest Proterozoic strata. In that golden age of paleontological discovery, it was certainly a possibility, and one to inspire exploration for decades to come. And in 1905, the British geologist William Solas offered yet another explanation for the Cambrian explosion, justifying why Precambrian animal ancestors might have thus far proved tricky to find. At that time, the Cambrian fossil record consisted almost exclusively of animals in possession of shells. The trilobites, brachiopods, sponges and echinoderms whose mineralized remains are less ravaged by decay, and which can more easily survive the transformation from sedimentary detritus to coherent rock. Could it be, he pondered, that this was the real innovation that caused the Cambrian explosion? That the beginning of the Cambrian wasn't the moment that all animals appeared, but rather when they evolved the ability to make shells and withstand the fossilization process. And this was a proposition that at least had some evidence to support it. Solas noted that the further back one goes through the Cambrian, the smaller, thinner, and more delicate the shells of those primitive animals become. It seemed logical that prior to that explosive moment there were animal ancestors. But they were soft-bodied, juicy, and quickly devoured before they had any hope of being preserved. However, the last 100 years of paleontological discovery hasn't quite unfolded the way these scholars predicted. New fossil beds have been discovered all over the world, but the bounty they contain has served only to compound the Cambrian conundrum, not resolve it. Walcott himself was complicit in discovering a new fossil assemblage, high in the Canadian Rockies of British Columbia. Dating to the Middle Cambrian, the Burgess Shale contains intricate flattened fossils of the most bizarre animal fossils, preserved as thin organic and phosphatic films between layers of grey slate. These fossils are almost exclusively soft-bodied, without a shell in sight, and their discovery served to dismantle Solas's argument that fleshy animals would be missing from the fossil record. Other such examples of exceptional preservation have since been found throughout the latest Proterozoic and earliest Cambrian periods. In China, the Miaochanshan shales date from the early Cambrian, around 515 million years ago, and contains similarly flattened fossils of soft-bodied animals, this time preserved by fine clay minerals. The so-called Chengjiang biota offers a valuable window into some of the earliest Cambrian animal ecologies, including a diversity of chordates, the group that would eventually give rise to us. From the 1950s, strange impressions in sandstones were uncovered in England and in Australia, and soon became recognised as an entirely new fossil assemblage, dating to that critical time just before the Cambrian explosion. But these Ediacaran fossils, who now boast representatives from Russia, Canada, Namibia and elsewhere, looked nothing like the animals that we know today, and bear none of the distinctive characteristics that would ally them with one of the 24 phyla that appeared later. They may have been life's first experiment with multicellularity, but they were nothing like the missing links that Charles Walcott imagined. In fact, the modern paleontological inventory contains more than the late 19th century scientists could have ever hoped for, with countless examples of exceptional preservation, unprecedented resolution of stratigraphic relationships, and precise isotopic dating of rocks 500 million years old. Geobiologists have been able to chart the progress of early animal evolution with pinpoint precision. They have seen how the earliest experiments in body plans resolved into a common theme of bilateral symmetry, something still seen today in everything from worms and mollusks to us. They have shown how the entire Cambrian ecology was transformed by the invention of burrowing and swimming, as revealed by the traces left behind by wriggling and scurrying creatures that disturb the sediment in brand new ways. And they have finally done what those geoscientists tried to do in Prague in 1968, and have definitively established the boundary between the Precambrian and the Cambrian, and mark the moment that the Cambrian itself began. The advent of vertical burrowing. This wealth of information helps to unpack the events of the Cambrian explosion moment by moment. We now see how animals diversified and radiated in a stepwise fashion throughout the early Cambrian. We even see groups becoming extinct before the explosion itself is over. It is as if we are peering into the rolling clouds of a physical blast, seeing the ever-changing blooms of material expand and diverse, tracking the paths of shrapnel through the fog. In a period that is biologically long and yet geologically short, the diversity of animal life blossoms as the newly invented forms come to dominate the oceans. The fossil record is certainly not lacking, but for all of this incredible resolution, the picture still freezes before the moment of ignition. We see the expanding blast and the Phanerozoic aftermath, but we still cannot clearly see the beginning, or most critically, the cause. The explosion of animal life may not be instantaneous, but it appears to be real after all. And so we are left still needing to identify the agent of miraculous creation. Was there some extrinsic factor, some new configuration of Earth, ocean and atmosphere that primed the world for revolution? Or was it something unseen within the organisms themselves? An intrinsic switch that opened the door to unprecedented innovation. tectonic plates move. Deep in the earth, vast unseen forces collude to jostle the fractured slabs of solid rock that make up the fractured armor of our planet. Ancient continents are torn asunder and unceremoniously piled together again, folding and crumpling over on themselves in tortured heaps. And as mountains rise, their roots plunge deeper into the upper mantle, bearing not just the crushing force of inexorable collision, but also the weight of some 70 kilometers of towering rock, and the intense heat of the semi-solid mantle that swirls in slow motion around their inverted, craggy bluffs. It is a place of extremes, where solid rock reaches the highest temperatures and pressures to be found in the Earth's crust. And it is a place where time capsules are created. Because deep in these Titan mountain forges, silicon, oxygen, and the metal zirconium are fused together into intricate lattices to shape elegant, pale yellow faceted crystals of zircon. Each strike of the metamorphic hammer, each convulsion of the planetary pileup leaves a trace in these growing crystals, like tree rings that tell tales of environmental boom and bust. In time, the collisions will cease and the mountains will begin to erode away. With their upper layers stripped away, the hearts and roots of the range will rise, buoyed by the dense mantle below. Eventually, those torture-forged zircon crystals will be exposed to the air as well, where they will be pried from the rocks that embrace them by wind, water and ice, to join detritus in the sandy mountain streams, which carries the mountain itself away, grain by grain. Much of that mountain sand won't even survive the journey to the sea, before chemical alteration and physical abrasion sees it transformed or obliterated. But the zircons persist. They are tough and utterly unreactive, so they survive transport, deposition, even lithification that traps them inside new, sedimentary rocks. These minerals retain their faceted structure, their tree-like rings through hundreds of millions of years of geological formation and destruction. And they persist to this day. In sediments or in sedimentary rocks, geologists find these precious mineral time capsules dating back to the very beginning of our planet's history. With the radioactive isotopes that can date them, and the ringed zones that tell of their formation, they are tiny crystalline windows into immense crustal upheaval. There are zircons around today that span almost the whole of Earth's history. But there is an unexpected absence of specimens that are aged around 500 million years old. This bountiful collection of time capsules from around the end of the Proterozoic point to a period of unprecedented mountain formation. A time when mountain roots grew deeper and wider than ever before, and were matched on the surface by supermountains. the sheer scale of which has never been seen on Earth before or since. Is it mere chance that this extraordinary period of tectonic turmoil coincided with the greatest evolutionary leap our planet has ever seen? Or could these end Proterozoic supermountains be somehow linked to the events of the Cambrian explosion? It isn't unreasonable to consider environmental transformation as a principal driver for evolution. After all, it is often new environmental pressures or opportunities that force the hand of natural selection, leading to innovation that helps organisms adapt and thrive in their habitats. Indeed, the high-resolution fossil record we now have from the earliest Cambrian strata show that the evolutionary advancements of the so-called explosion didn't happen everywhere all at once. In some places, evolution raced on ahead, while in others, it stalled, biding its time before the new innovations arose. And that may simply be a consequence of the environments that prevailed. In modern and ancient oceans, warm, shallow waters, such as those found around the fringes of continental shelves, are linked to biological success. Larger body sizes, greater diversity, advanced ecological interactions, and more intricate biomineralization are all characteristic of these azure waters. The glorious atoll communities of the Red Sea, the Barrier Reef, and the Caribbean Keys are all testament to the bounty of these shallow, sunlit paradises. So it has been suggested that the incursion of seawater onto the early Cambrian continental shelves, perhaps as a result of global sea level rise or the reshuffling of continents, was enough to create Edens all over the world. Allowing early animals to thrive, innovate, and evolve. Indeed, it helps to explain the staggered arrival of new animal forms at different locations around the globe, as different shelves were flooded in sequence. But it does little to explain the origin of the animal groups in the first place. The sea has invaded continental shelves many times throughout Earth's history. And while it may have created more clement conditions in which life can thrive, it does not typically lead to a radiation or diversification of that life in and of itself. No. While the newly made animals may have found a comfortable home in the lagoons of the early Cambrian, it was probably not those lagoons alone that created them. Instead, it was likely another, unseen feature of the shallow, sunlit paradise that drove the biological innovation at the beginning of the Cambrian. Because waters shallow enough to be kissed by the sun are also shallow enough to exchange oxygen with the air. It is oxygen in the water, rather than mere warmth or calm conditions, that has the power to supercharge life. It is oxygen which, in modern and ancient waters, leads to bigger animals, more elaborate shells, higher mobility, and more predation. It is oxygen that opens the door to biological innovation, and it is oxygen which, up until this pivotal moment, has been lacking in the late Proterozoic Ocean. The gas, which we have come to consider essential to all life on Earth, has had something of a checkered history on our planet. Completely lacking from the oceans and atmosphere for the first 2 billion years, its debut around 2.4 billion years ago, thanks to the newly invented photosynthesis, was met with catastrophe in the living world. Life forms that had no need to evolve resistance to the reactive gas now found themselves asphyxiated and smothered by this new, invisible toxin. The very photosynthesizing organisms that produced it as a byproduct were slaughtered en masse by their own waste. With oxygen in the shallow water and atmosphere, the entire Earth transformed, shattering warming greenhouse gases and plunging the Earth into a frigid glaciation through which much of life was unable to weather. By the time the planet had emerged from this big freeze, microbial life had learned to protect itself from the damaging gas, allowing photosynthesis to continue among cyanobacteria and eukaryotic algae, and allowing oxygen levels to stabilize alongside Proterozoic life. But those levels were a far cry from the oxygen we enjoy today. With only microscopic contributors to the gas's reservoir, concentrations reached little more than 10% of modern levels, and many scientists believed that this alone was enough to impede the development of any larger, more complex, or more mobile life. But something changed in the early Cambrian. Tracing the record of oxygen through time is not always straightforward, simply because the gas is so reactive and often doesn't stay where it's put, whether that be in water, sediment, or air. So researchers must instead search for clues from other elements, like carbon and sulfur, whose cycling through the Earth is fundamentally different when oxygen is or isn't present. And sulfur and carbon isotopes trapped in ancient rocks whisper of intriguing changes in oxygenation around the end of the Proterozoic. The newest data points to more widespread oxygen in the atmosphere, as well as discernible pulses in oxygen in the ocean linked intimately in time to the radiations of life during the Cambrian explosion. This is the very relationship that's seen in more modern ecosystems, echoed down through the ages. With more oxygen around, cellular metabolisms have more fuel for their furnaces, more opportunity to experiment with bigger growth, greater complexity, and more extravagant mobility. And so, many scientists are happy to ascribe the diversification of animal life to more freely available oxygen at the beginning of the Cambrian. But the question remains, what caused that increase in oxygen in the first place? And that is where the zircons, the mineral time capsules that are uniquely able to withstand the trials of millennia, have something to tell us. Their abundance at that pivotal time tells of a rare and extreme tectonic event that saw the creation of supermountains that span the early Cambrian landmass. Larger-scale plate tectonic reconstructions reveal that, from around 800 million years ago right up until the beginning of the Cambrian, the continents of the world were assembling into a single immense supercontinent, Gondwana. The vast tectonic forces that drove that continental pileup were responsible for raising the so-called Transgondwanan supermountains, reaching more than 5 kilometers high, 1,000 kilometers wide, and 8,000 kilometers long. This mountain range stretched some twice the length of the United States, 20% of the circumference of the globe, and it had a profound effect on the planet. Because the assembly of Gondwana also saw the creation of huge volcanic chains, pumping out vast quantities of carbon dioxide into the atmosphere. Extra greenhouse gas led temperatures to rise, accelerating the process of weathering at the very same time that plate tectonics was providing ever more raw material that could be weathered. Over millions of years, wind, water and ice ground the Transgondwanan supermountain down to mere sand and mud, enough to cover the entire United States more than 10 kilometers deep. But all that detritus didn't stay on land. It was washed into the oceans as a fertilizing plume for waiting phytoplankton to feast upon. With such a banquet, green algae and cyanobacteria bloomed, creating a significant uptick in photosynthesis worldwide, releasing oxygen into the shallow ocean and atmosphere. That oxygen, which came about ultimately because of motions inside the Earth, then became the driving force behind a burst in animal evolution. It is certainly a neat explanation, and one that is sure to appeal to every kind of geoscientist, since it involves every part of the Earth's system, from hard rock to climate to the living components of our world. While the Transgondwanan supermountain may have been impressive in its extent, it probably wasn't the first or last of its kind. Continents have piled together into massive supercontinents several other times throughout Earth's history, with associated volcanism and mountain-building events. But tectonic upheaval isn't always met with dramatic rises in oxygen levels, or with unprecedented leaps in evolution. Likewise, oxygen levels have had stepwise increases and fluctuations throughout geological time, but they haven't always been linked to tectonic turmoil or to animal radiation. Of course, there is yet another possibility. One which requires us to challenge the seemingly obvious and question our base assumptions. There is no denying that the unmatched radiation of animal life at the beginning of the Cambrian coincided with a rise in atmospheric and oceanic oxygen levels. But that does not intrinsically imply that the oxygen caused that burst in evolution, merely that the two are coincident in time. In fact, it could be that the relationship is turned on its head, and the bursting forth of life itself caused the rise in oxygen levels. Animals don't have the same capabilities for producing oxygen as their photosynthetic plant and algal cousins, but they do still have ways to modify their environment. Recalling that the first moments of the Cambrian explosion were marked by the advent of vertical burrowing, the appearance of animals also saw an unprecedented disturbance of seafloor sediments that had, up to this point, been little more than a passive chemical reservoir. As newly mobile, burrowing animals dig down through ocean sediments, they are the ones who release the nutrients trapped within, offering fuel for the photosynthetic life that lingers at the sidelines, allowing them to share in the success and produce more oxygenic waste in the process. In this theory, it must be animal life that came first, and the oxygen rise second. We may not ever definitively be able to know from the chemical whispers contained within the rocks whether it was the geologically mediated rise in oxygen that spurred on animal evolution, or the modification of geological environments by animals that caused the rise in oxygen levels in the early Cambrian. Perhaps both mechanisms were in play, reinforcing one another to accelerate diversification and animal radiation across the world. And yet, the environment of the early Cambrian alone cannot fully explain the beginning of the Cambrian explosion. The reason why animals appeared in such numbers and variety in the first place. It is unlikely that environmental oxygen was enough to light such a fire under the backside of evolution without something else at play. Some mechanism that loaded the barrel and guided the hand of natural selection to light the fuse on the Cambrian explosion. It was 1950 when Alan Turing, flushed with optimism about the capabilities of the new mathematical computer, first contemplated a future in which such computers could think for themselves. In his mind, he saw them solving problems and making decisions just as a human would. He foresaw a time when the products of computers would be all but indistinguishable from those of living, breathing humans, giving his name to the test that would aim to make that distinction. Unfortunately, the room-filling computers of the time were a long way from being able to realize Turing's heady imaginings. Little more than extremely expensive, bulky calculators. Most were incapable of storing commands with which to make those decisions, let alone conduct the natural language conversation that the Turing test was based upon. The following decades saw vast improvements in computer hardware and software. Processors became smaller, operations became faster, and memory capabilities became vastly greater. Neural networks, which connected commands into a cascade similar to our own biological brains, promised to advance the art of artificial decision-making. Soon, the idea of artificial intelligence didn't seem so far away, inspiring works of fiction that foretold the downfall of humanity at the hands of our digital masters. In 1970, computer scientist Marvin Minsky predicted that computers could attain a general intelligence equal to that of a human in 3 to 8 years. But But among these optimistic predictions and the ever-present fear of an imminent sentient robot revolution, the reality never quite managed to live up to the AI promise. It became clear that such a general intelligence that Minsky imagined would require computational power millions of times greater than that what most processors could muster. Alan Turing would most likely have been disappointed with the jilted, glitchy conversations that were the result of even the most complex neural network. Rumors of our imminent downfall, it seems, were greatly exaggerated. And the dream of generally intelligent computers faded, along with interest and funding for its research. But in the last decade, while we were all looking the other way, artificial intelligence has experienced something of a surge in success. In the era of big data, in which information about everything is available and shared thanks to the internet, modern artificial intelligence's machine learning algorithms allow it to learn from that data, finally giving them the tools they would need to make a decision just as a human would. The 2020s so far have been defined by advances in AI, and with computers beating humans at chess and Go, they are now taking on humans at their own game. ChatGPT has suddenly, explosively achieved what Alan Turing always dreamed a thinking computer would, in producing a wealth of AI-generated content that is all but indistinguishable from man-made works. The pace of AI development was slow, at times seemingly non-existent, but the incremental developments that were made in the shadows accumulated gradually. Suddenly, and without warning or fanfare, an extraordinarily powerful AI algorithm existed. And because of the nature of computing today, it is everywhere. This was a revolution, a seemingly miraculous act of digital creation that mirrors the explosive moment of animals' arrival during the Cambrian explosion. Just like AI, there seemed to be a whole lot of nothing going on, until suddenly, and without warning, fully formed animals appeared and were immediately successful. Could it be that, like their digital counterparts, animals' underwhelming predecessors were slowly accruing new innovations that readied them for their moment in the limelight 540 million years ago? It's very likely that the developments that led to the Cambrian explosion will always remain hidden to us. Much of the stuff that makes an animal, such as their cell structure and genetic makeup, are elements that do not really enter the fossil record. Even the highest fidelity cellular fossils, preserved in finely crystalline clays and phosphate, fail to retain true information about the chemical and biological makeup of those cells. As such, scientists are left speculating based on what the fossil record can tell us, and what we can discern from the cells and genes of existing animals and their close relatives. One such speculation, wild though it may seem, is that cancer, one of the most destructive phenomena in multicellular organisms, may have been key to their appearance in the first place. We've already seen how a rise in atmospheric and oceanic oxygen coincided with the rise of animal life. This makes sense on the scale of ecosystems and entire organisms. Since oxygen is the fuel for our biological power plants, an increase in that fuel means an increase in output on all fronts, from size to mobility. But on a cellular level, the appearance of complex multicellular animals alongside an oxygen rise is counterintuitive. Stem cells, which are the versatile, so-called pluripotent cells from which all of our specialized tissues develop, behave in the opposite way to how we might expect in the presence of oxygen. When oxygen concentrations are low, stem cells replicate quickly, creating more cells more rapidly. However, when oxygen levels are high, the stem cells mature, and their replication slows down. In this way, oxygen actually becomes a hindrance to multicellularity, making it all the more surprising that complex macroscopic animals even could evolve during the times of rising oxygen in the early Cambrian. However, there is one way in which cells circumvent this shutting down of stem cells, and that's in the formation of tumors. Cancerous tumors arise from cells with broken DNA that essentially fools the machinery of the cells into thinking that oxygen is low, even when it's not. Under what it believes to be immature, low oxygen conditions, the cells replicate unchecked, growing out of control and creating the kinds of tumors that can take over normal tissue and spread beyond their origin in search of more space to expand. In a fully developed modern animal, such tumor development can be extremely damaging to the highly tuned bodily functions, and is ultimately fatal. But in those burgeoning animal ancestors first experimenting with multicellular ways of life during the late Proterozoic, this kink in the genes could have given biology the nudge that it needed to succeed despite the rise in oxygen. With a cancer-like mutation of the ancestral stem cells, these key components of a multicellular body could have remained immature and pluripotent, and kept on replicating out of control, even when elevated oxygen levels would have otherwise shut them down. Today, cancer kills, but in the early Cambrian, it might have been the very thing to give animals life. But there are other breadcrumb trails to be found within the unmutated DNA of animals which can hint at their development too. Could these shed light on the explosion of animal life? There are certain specific genes that are needed in the instructions for making an animal, such as those which tell cells to stay stuck together, those that instruct cells to differentiate and perform certain functions, and those which coordinate the intricate dance that is animal immunity. Phylogenetic trees of life that reconstruct the relationships between organisms, and molecular clocks that trace the gradual appearance of genes over geological time, reveal that some of these animal-specific genes actually predate the appearance of animals in the fossil record. However, others appear for the first time during the Cambrian explosion, alongside the animals that they encoded. And so, genetic scientists today are faced with much the same conundrum as Darwin 150 years ago, in trying to trace the origins of animal genes, and explain how so many could appear so suddenly. Ultimately, the DNA inside our cells is subject to the same evolutionary pressures as the characteristics that they program, with changes occurring naturally and natural selection favouring those which work best for the organism. So we might expect the animal-specific genes to have evolved gradually over the latter part of the Proterozoic, perhaps being derived from genes that served their unicellular ancestors. But some scientists believe that the genes themselves, and their animal manifestations as a result, really did spring up faster than normal natural selection would countenance. Some extraordinary genetic event that kick-started animal evolution from a molecular level. Some will claim that extraordinary events require extraordinary triggers. And there's not much more extraordinary than the viral panspermia hypothesis, which invokes an extraterrestrial source for the genetic novelty that kick-started the Cambrian explosion. Our planet is constantly being bombarded by material from the stars. Relativistic particles that bounce off our magnetosphere and create stunning auroras, micrometeorites that burn up in the upper layers of the atmosphere, and, according to some authors, intact genetic molecules capable of transforming life on Earth. Panspermia is one of the many hypotheses put forward to explain the origin of life on our planet. Through seeding of cosmic organic molecules or even entire extraterrestrial microbes. So viral panspermia as a mechanism for the Cambrian explosion is merely an extension of these ideas. If viral-style DNA is circulating freely through the cosmos, then that novel DNA may rain down on our planet, survive its descent, and infect the eukaryotic life in Earth's oceans. With an injection of alien genes, life could leap forward at a rate unseen at any other time in history, and create life forms the like of which had never been seen before. It is certainly an evocative idea, but unfortunately it's rather unlikely and somewhat difficult to prove. There is nothing in the animal genome today that hints at a cosmic origin, and although simple organic molecules have been detected inside interstellar gas clouds, even our best telescopes have failed to identify anything that might be a genome-altering virus beyond our planet. But there is yet another possibility for this leap in genomic evolution. One that doesn't require alien invasion. In the animal genome today, homeobox genes help to shortcut the instructions for building a body by providing a kind of body plan template. They are a kind of higher-tier instruction that encodes large-scale anatomical features, like a leg or an entire body segment. And scientists first explored the function of Hox genes in fruit flies by making small changes to the DNA code, which caused the fly to grow a leg from its head in place of an antenna. So some scientists speculate that these homeobox genes could have been very powerful during the diversification of animals during the early Cambrian. With an easily editable template, an animal wouldn't have to gradually evolve all of the genes required for growing a new leg or body segment. They would need only acquire a mutation that duplicated the entire segment. In this way, animals could copy and paste the appendages that they already had, to experiment with brand new body shapes. With tweaks to the homeobox template, it's not hard to see how animals could suddenly and spectacularly diversify, with the successful new body plans living on to found the major animal phyla. Indeed, it's conceivable that it was the evolution of homeobox genes in the first place that provided the first spark for the Cambrian explosion. However, the origin of these genetic sequences is not clear, and at least some of our homeobox genes are also shared by plants and fungi. Like so much of this pivotal time of our evolution, the chronology is muddied and may never be fully revealed. Our understanding of genetic evolution is better than it ever was, but it still leaves a lot to be desired. The murky history of homeobox genes is only a symptom of a deeper lack in understanding about the molecular machinations that underpin evolution. perhaps an extraordinary explanation is needed for the surge in genetic evolution at the time of the Cambrian explosion. Or perhaps this is a normal state of affairs during times of ecological upheaval. In other words, perhaps it was the environmental pressures and opportunity that accelerated the genomic change, rather than the genetic evolution leading the way. But what changed in the ecology that could have spurred such a dramatic revolution? When considering the excitement of the Cambrian explosion, it's easy to forget the other players on the vast living stage. Even while Ediacarans rise and fall, and the first animal phyla take their tentative steps on the muddy sea floor, the oceans and even the nearshore land surfaces are teeming with life. Up until this point, photosynthesizing cyanobacteria and eukaryotic algae have been the main event for life on Earth. And it's possible that it's their interactions that kick-started the emergence of animals. In what has become known as the slime theory of the Cambrian explosion, researchers think that the outcome of territorial battles between prokaryotic cyanobacteria and eukaryotic green algae was what opened the door for the evolution of animals. Even after the first eukaryotes evolved, at some point during the Mesoproterozoic, they were still vastly outnumbered by the cyanobacteria. These prokaryotes thrive thanks to their simplicity, packaging the machinery of photosynthesis into the most basic possible cell. They do well for themselves, but cyanobacteria don't give much back to the ecosystem. Swallowing up nutrients and only releasing them when they die, already buried in entombing sediment, there is little left behind to support any other life. But things change around the time of the snowball glaciations at the end of the Proterozoic. Here, scientists find a surge in molecular fossils that could have only been produced by eukaryotic algae. This patchy record tells of a time when, finally, cyanobacteria's chokehold on our oceans was broken, allowing photosynthesizing eukaryotes to become dominant for the first time. To the casual observer, the difference may seem minor, but the more complex cell structure and metabolism of a eukaryote offered a great deal more to the rest of the ecosystem. Now, there were energy-rich cells worth eating, and nutrient stores that could be effectively tapped into. For the first time, there were food chains and webs with something substantial at their basis. Eukaryotic productivity shifted the pace of ecological turnover and opened a door for more energy-hungry life to thrive. With more energy available to the simple consumers of the late Proterozoic oceans, the community enters into a runaway cycle of positive feedback. Early animals can move more than ever before, exploring their environment and learning to burrow down into the sediment. This first foray into ecosystem engineering transforms the two-dimensional Proterozoic world into a three-dimensional Cambrian one. With all the additional opportunity that a new dimension can offer. New niches open inside the sediment and the water column, and organisms invent new ways of living. Zooplankton, tiny living animals that can float in the water and make the most out of the algal producers there, provide links between the seafloor and the open ocean. And for the first time, higher organisms can evolve to prey upon these lesser animals. With predators and prey comes an arms race of defense and attack, leading to the appearance of mineral armor and weaponry in the form of protective shells and hardened mouthparts. Eventually, for the benefit of both predators and prey, eyes evolve as well. From a simple change in the kind of slime on the ocean's surface, the mere machinations of nature and natural selection are able to do the rest. Whether this ecological transformation would have been enough to drive genetic revolution itself, whether the genetic blueprint was in place, or whether there were other factors, either extrinsic or intrinsic, at play, it's hard to know. In reality, it is very unlikely that there was ever a single thing that caused the Cambrian explosion, but rather an accumulation of factors that created a cascade away from an old microbial equilibrium and towards a new multicellular one. Big evolutionary events like these need not require a big evolutionary cause, but merely an accumulation of favorable conditions and a nudge in the right direction at the right time to tip the balance. As with the dramatic explosion of artificial intelligence in recent years, it begins with the gathering of small, seemingly unremarkable changes. By themselves, they aren't enough to transform anything, but they inch us ever closer to a tipping point. We may not know when or how the breakthrough will happen, but one final innovation is enough to send the whole system over the edge, shifting the paradigm and creating powerful AI, or creating a new kingdom of life, and ultimately changing the world forever. The Cambrian explosion has only ever happened on Earth once, and so we have nothing to compare it to, no other points of reference. In this, we are as ignorant of the origins of animals as we are on the origin of life itself. More than 150 years on from Darwin's tortured contemplation of the Cambrian explosion, we have more knowledge and more hypotheses than he could have ever dreamed. But we are perhaps still no closer to knowing what one thing, if any one thing, caused the sudden appearance of animals on Earth. Perhaps we never will. You've been watching the entire history of the Earth. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.